Hello everyone. In today's session, we will be looking at power performance and area analysis using VisualSim Architect. The overview for today's session includes system level methodology for power performance and area trade-off, where we identify areas for power optimization and also analyze the impact of power states and management decisions on performance. We also generate early thermal and battery metrics for system designers who can use this data to make early architectural decisions. We also enable the various design teams to be integrated using a single modeling platform. The current power performance area analysis methods include the manual and spreadsheets to provide worst case values only. And these design approaches are often separated, meaning that there are teams working on performance analysis and separate teams working on power exploration. This means that this is a disjoint operation. The power metrics for complex use cases and current operations require time-based exploration, so which is not provided by current approaches. The dynamic changes in voltages, the LTO efficiency, instruction drive, and transition times are not considered in the current approaches, which is a huge limitation. Also, the current approaches cannot measure task or application level specific power, which means, let's say we have 10 tasks and we cannot identify the specific task or application which contribute more to the power consumption. If we can identify that, then we can make optimization just focusing on that specific application, which makes the whole process a lot easier. And this is the agenda for today's session, which the overview has already been covered. And the power modeling approach will be looking at, and we'll be looking at how to get the data that is required to model power. So we'll be using the datasheet from vendors as one option. And as another alternative, if in case we are not able to identify the data sheet from vendors, then we can make use of online sources from reputable sources. And then we will look at how the power modeling for custom IPs can be done, where we can, let's say we want to build our own custom IP, and if we need to add power tracking capability to it, then how can we do it? We'll be looking into that as well. And then we conclude today's session. So first, let us consider a multimedia SOC. So we have ARM Cortex A53 core. It has shared L2 cache. It also has a hardware accelerator. It makes use of AMPA AXI buses, and it has DDR4 DRAMs. So for this multimedia SOC, we start off with specifying two requirements. One is the power target that needs to be achieved, which means that the power consumption for the whole SOC has to be below 1 watt, the average power consumption. And on the performance side, the number of frames in 2 milliseconds has to be greater than 10,000. So these two targets has to be achieved by this proposed multimedia SOC design. So we'll be making use of VisualSim Architect to implement this design and try different use cases and analysis to make sure that these targets can be achieved. So this is the assembled VisualSim model of the SOC architecture, and where we have mapped the MPUG application to the ARM subsystem. So here you can see on the top part, we can see the hardware architecture, where we have the ARM subsystem, hardware accelerator, the system bus, which is the AMPA AXI bus, the DDR4 controller, and the memory. And we can see the ARM subsystem is zoomed in here, and we can see the ARM Cortex A53 cores, shared L2 cache, the bridges, and the buses to the next level. And in the bottom half, we can see the software architecture that we are running on top of the hardware architecture. So here we can see we have multiple use cases defined, and the specific use case of focus here will be the scenario 2, which will be the bottom sequence. So we have the sensors generating frames, then we read the frame, we decode the frame, we do video post-processing, we render the frame, we do format conversion, and then rotate the frame, and then we display, and then we plot the results. So now, since we now that we have looked at the hardware architecture, the software definition, we'll be now looking at how we can model power. So it is done. One of the primary components that is used for this purpose is the power table. So here we have a power table, and the screenshot next to it shows how the power table is filled up or updated in such a way that the power for all the hardware devices are accounted for. So as we can see, the power table has different parameters, and each has its own specific purpose. So the next consecutive slides, we'll be looking at each of the parameters of the power table and how they need to be updated so that the power can be tracked for our target application. So here we have the power state table entry. First, we start with the manager name parameter, which is over here. And this is the unique name for this power manager. So the unique name that we have entered right now is manager_1. So this is the unique name for the power manager. And then we have the manager setup. So here we'll be looking at first 5 columns specifically. So we have the architecture block column. This is where we list the devices supported by the power table. So here we can enter the devices which are supported by default, which means the VisualSim Architect by default supports a certain list of modules to track the power. We can also add custom IPs in this architecture block column if we have them. So also a device can be divided into multiple subcomponents with a unique line for each. So this means that if we have, let's say, for example, a DRAM device, then we can have multiple lines for that device itself. For example, in the previous screenshot, we can see there are multiple lines associated with the DRAM. We can see activate simple, activate standby, activate active, then the write power, read power, then the refresh powers. All of them for the particular DRAM has been listed in different lines. So if we need to have multiple lines associated with a single device, then that can be done as well. Then we have multiple power states associated with each device. So we'll be looking at the minimum list. This should be there for almost all the power tables. So we have the standby state, active state, wait state, and idle. So the active state corresponds to the power consumption when the device is in idle. So it is not essentially doing any work, but it needs to go back to active state very soon. So that is standby state. The active state is the power consumption of the device when it is processing a task, which means it is busy or it is in run mode. Then we have the wait state. It means that it is the power consumption of the device when it is waiting for a response. Now, if we consider a processor core, let's consider that it has sent out a request to the instruction cache, and there are no other instructions being executed in the pipeline, which means that for the processor, it doesn't have anything else to operate on, and it must wait until the instruction returns from the iCache. So then at that duration, it will be in wait state, and during that time period, it will be in the wait state. Then we have the idle state, which means the power consumption during off state of the device, which means it is fully turned off. And we can see here for various devices, we can see for the ARM1 core, ARM2 core, we can see how each of the state values are calculated. So we can see that for certain devices, it is a static value. And for some others, it is linked to a variable. So these are variables which are defined in bottom part of the power table. We call the expression list. We can see they are defined in the bottom part called the expression list. So which means that these state values can be static or dynamic. So during simulation, these state values can change depending upon the variables that we have linked, or we can either model it as the static value itself. Now we'll be looking at the transition details. So we have the operating state where we have three columns. One is the existing state, the off state, and the on state. The existing state defines the initial state of the device. So when we start the simulation, what is the state for each of the device? So by default, every device will be in standby state by initial. Then we have the off state. That is the off state of the device. So that is also defined to be a standby state. Then we have the on state, that is the active or on state of the device. We have set it to active state. So this means that we are linking it to a state column here. So when it says that it is standby, it will go and read the standby column value for that device. Then we have the state transitions, which looks at the T on off column. This is the transition time delay from moving from one state to another. So this is the delay, which means that we cannot change from one state to another in zero time. It needs some time, some delay to move from one state to another. So this value can be modified dynamically as well, which means that we can, instead of specifying it as 1.0 e minus 8, we can link it to a variable which can be updated during simulation. So this delay for the state change will vary during simulation. Then now we have the powerTable parameters, which are essentially the additional columns in the table. So we have the megahertz column where which is used to specify the clock speed of that particular device. So here we can see for the first two, for the ARM processor cores, we have linked it to a parameter. So it is linked to a parameter. When we change the parameter value, this column value will be also be updated. So we can add more columns, and these column values can be dynamic as well, which means they are linked to variables. Now we have the power management and the dynamic compute section. So this power management, or the delay to state change, is the power control state machine that changes state if the device has been in a particular state for a period of time. So this means that, let us consider this example here. Scheduler hardware engine stand by 1.0 e minus 3 or 1 millisecond and idle. This means that if the scheduler hardware engine is in standby state for more than 1 millisecond, then more than or equal to 1 millisecond, then we have to move or change the state of scheduler hardware engine to idle. So which means that we are moving from standby to idle state if it is in standby state for more than 1 millisecond. So this is a kind of a power management or power optimization that can be done using this powerTable. So this is very same as, for example, we have the laptop, and if the laptop is not being used for, let's say, 5 minutes, then the laptop screen can be turned off. Similarly, the same kind of operations can be done using the delay to state, change state parameter section. Then we have the expression list, which is used to define expressions for state values and can be computed dynamically. So we can see here that we can define various variables as one of the column that is under the name column, and the value for it can be defined in the value column. So here we can see we can define a static value again here, or it can be linked with another variable. So we can make it in such a way that it changes dynamically. So during the simulation runtime, these values get updated, and as a result, these variables get updated, and the corresponding state gets updated as a result. Now we will look at how we can configure the powerTable. How are we going to get the values for the powerTable entries? So the minimum information that is required are the list of states and associated power values for each of the device. The power values can be a double data type or a complex expression that has variables included in it. So now for each device, we have to define the power in watts, milliwatts, or microwatts for all the states that we want to include. So active state, standby state, idle state, wait state. we have to include all of them. So we need to identify the power in watts, milliwatts, or microwatts. So how can we get the power value for each of the state? So this can be sourced from a vendor data sheet. So we can get the information from the vendor data sheet, or if we are not able to get the data sheet from the vendor directly, then we can look at research papers, journals, articles, and blogs for specific scenarios and voltage and processes. So we can use that data from these articles, from these online resources, and update the table. Or we can count the number of switches and gates used in each process and multiply it with the power per switch and gate. We can scale it up. And the another option is, if you are doing a comparative case study, then we can use an approximate value for each state, because accuracy is not that important, because we are doing comparative case study. So since we are doing the comparison using the same platform, even if the accuracy is not 100%, it is not an issue. It is okay. So now, as we will go in detail and we will look how, using a data sheet, we can define the power table. So first of all, we need to identify the list of IPs or subsystems that are used in the SOC. So then after identifying them, we have to go and look for vendor specific details on them. So in our specific multimedia SOC use case, we have ARM Cortex A53 subsystem, which has L1 cache, local buses, L2 cache. We have hardware accelerator, a GPU. We have AMBA XA bus. We have a DDR4 DRAM. So for our analysis, we have looked at different vendors which are using A53 cores. So some of them include Samsung, NXP, Qualcomm, Amazon, Microchip, AMD, and so on and so on. So we have to look at each of these vendors' website and try to get the data sheet which covers these subsystems on a majority scale. Even if you are not able to identify all of them, it is fine. We can just combine the data from multiple data sheets. So we were able to, in this particular use case, we were able to identify a datasheet from NXP, the document number being IMX8M DQLQ IEC, and the source being provided here. So within this source, we were able to obtain details on the power architecture and the necessary details required to set up the power table. So we will take a quick look at the power table. And here, the details on the document. Here we can see the document, and we scroll up and we can see how the power architecture is defined. We can see the ARM Cortex A53 platform, GPU. We can see the DRAM controllers, DRAM files, all defined here. And here we can see the tables. We have the voltage table, and at the as we scroll down, we can see the current, max current supply table is also there. So as we get the voltage and current detail, we can calculate the power by multiplying voltage and power. So yeah, so we captured the voltage and current values from this document, and we update the table accordingly. So for example, we make use of the typical voltage values. We make use of typical column, the typical column. And for the current, we take the median. So since we have a range defined, we take the median value. So but for ARM core, since this diagram, we can see it defines 4 cores, but in our specific use case, we are only considering one ARM core. So what I have done is we divided the median by 4 to get the correct value. For others, we just took the median. So for the GPU, the median will be 1020, and for the DRAM, we again took the median. So accordingly, the values were identified. So here we can see there the table also gives value for a run state. We can see and idle state, the current value. So we make use of these current values to define the state power. So this idle, so we can see this idle state in the document corresponds to standby state in the power table. Okay, and the run state corresponds to the active state in the power table. So this power, this current values belong to active state, and this current values belong to the standby state value. So now we look at the updated power table using the NXP values, and we can see this is how the power table was updated. So the each of the entries, the ARM Cortex core is entered here, the hardware engine or accelerator is entered here, the hardware DRAM is entered, the DRAM block is entered here. Then we have the AMPA AXI power being entered here. We can see that for the standby, active, and wait state, it is all linked to a variable here. And each of the variables are defined with the power value captured from the current values captured from the document. We can see this is the current value current value for the active state for ARM core, current value for the active state for the GPU, current value for the active state across the AXI, and current value for the active state across the DRAM. And since for the DRAM we have three different currents, because we can see that it makes use of three supplies are essentially being used. We can see here we have the NVCC DRAM, then we have the VDDA DRAM, and then we have the VDD DRAM. We have four different supplies. So we have three different supplies. So we have three different entries for the DRAM supply. So we can see for the power, it is an addition of those values for the DRAM. So we can see for the power across the ARM core, it is the voltage across the ARM multiplied by the current across the ARM active state. So similarly, for the power, for the standby state across ARM is the voltage multiplied by the current across the ARM in standby state. So we make use of these equations here, and it is linked to these power states in the power table. Now we run the simulation when we map all the tasks to A53 core alone. So this means that all the tasks. So here in the model, we can see that here we have the software sequences. We have the sensor, read frame task, decode frame task, video post processing, render frame, format conversion, rotate frame, and display. All of these tasks were executed using ARM subsystem. We didn't use hardware accelerator at all in this use case. So so that is the first use case that is shown here. So we mapped all the tasks to A53 core. And as a result, we could see that the power consumption is within the requirements. Our requirement was that power should be less than 1 watt average power, and we achieve it because we can see the red dot in the graph is less than 1 watt. So it meets the requirement, but the performance requirement is not achieved because the maximum, only a maximum of 1.419 thousand frames were observed. And the total area was observed to be 442 millimeter square. So now we look at, in order to identify why the performance is not achieved, we look at the activity sequences. So from the activity graph, we could see that for all of the tasks, rotate frame task was found to be resource intensive because it takes too much of the resources, too much time of the A53 core was consumed. So what we did was the rotate frame task was mapped to hardware accelerator. So only the rotate frame task was run on hardware accelerator and others were run on A53 core itself. So now we can see that um, the power consumption has increased. We can see now it is above 1 watt. So the average power requirement is not met, but the performance requirement is achieved. We can see a maximum of 11.253 thousand frames were achieved in this use case. And we could also see that the total area has been increased because we added hardware accelerator. So it has went up to 457.8 millimeters square. So now, since the power requirements are not met, we are making some observations. Our average power consumption is greater than the threshold. And as a result, there are few options for the architect. We can use hardware accelerator from another vendor. That means we have to buy another vendor's product and include it in the SOC design. Or another option is use the same hardware accelerator, but apply power management technique. So because from the power plot for the hardware accelerator, we can observe that hardware accelerator is active only for a short period of time. So here we can see that in the previous slide, we could see the hardware engine was only active for short period, then it is not active. Active, not active. Active, not active. So as a result, we found that adding power management would be more efficient. So here we have a third use case where we map the rotate frame task to hardware accelerator and we added power management technique. So here we can see I am using the delay to change state parameter section of the power table to add the power management technique. So here power management for a hardware accelerator is applied if the hardware accelerator is in standby state for more than 1 microsecond, then we are moving it into idle state. And from the simulated result, we can see that the average power consumption requirement was met because we can see the average plot is less than 1 watt. We can see here 1 watt. And the performance requirement is also achieved. It is slightly affected because the maximum value is a bit lower than the previous maximum because of the power optimization technique that we apply. So now so we could now see that all the requirements were achieved by mapping the task to resource intensive task to hardware accelerator and by adding power management technique. Now, we also get a detailed power stats to make sure or verify that the stats from the simulated model matches with the datasheet value. So we can see that the active state values for each of the devices matches with the datasheet value. Standby state values are all matching with the required values. We can make sure of it by using these stats. We also get a file which is saved after the simulation gets completed, which contains the cumulative and the average for each of the devices. We also get a power state transition log display where we can see each of the update happening in the SOC power level. So here we can see it was at 0.573 watt. Then it moves to idle state. So then the power level goes below. So, and then it now in a scheduler hardware engine is turned on, which means it is active. As a result, the power has been increased significantly. So we can see the power state transition log for the whole SOC here, and we can also identify the device responsible for the power spikes using this window. And if we need a detailed power plot, then we can make use of the GNU plot. So this is also generated from simulation once we enable the state plot, and we can identify when each of the devices are active and in standby, and we can also verify the sequence of operation. So we can see when the ARM core is active, when the hardware engine is active, when the memory accesses are being done, when the bus is active. All those information can be seen from this detailed plot graph. Now, we will look at how the online articles and blogs can be used to define the power table. So this is an option if we are not able to get the vendor data sheets. So here the plan is we search for articles and blogs with results of experiments and benchmarking. So we have to look at online results. We have to search and identify material which discusses the results of experiments in detail. And then we convert the sample data into equation for the power table. So we get the data and then we convert it into some sort of equation which can be entered in the power table. Now, we have to make sure that we are looking at reliable websites or sources. So some examples are Anand Tech, Tom's Hardware, Tech Power Up, for Hardware, Foronix, etc. So here we are using the Anand Tech article or a blog as a reference to get the ARM Cortex A53 metrics. So in this article, they are benchmarking or evaluating Samsung Exynos 5433 device. So I will take you to this article. So here we can see the article that I have looked at. And we scroll down and we can see details, and we can see a graph where they have run different experiments for different frequencies and the power values for each frequency was recorded. So we use this data. This data was used and we imported it into an Excel sheet. So we have two columns, frequency column, power column, and we converted this data into a scatter plot and using the Excel features, Excel scatter plot feature. Then we use the equation to be displayed, and we could see the equation being listed here for this graph. So this equation is power, the y is power. So power equal to, and it is using this x is frequency. So this equation, we get the required equation, and this can be inputted into the power table. So here we have the updated power table. And here we can see for the ARM Cortex A53 core, the standby active states, we can see how they are calculated. So the same equation, 2.0 E minus 19 into processor speed, megahertz, the frequency, it is being used. It is being linked, and the same equation is being used in the power table. So this is how we made use of Samsung Exynos data samples to update the power table. Now, if we want to, so it is possible that we want to model custom IPs, and if we want to do the power tracking or power modeling for custom IPs, then we make use of power regex functions. So a regex is a collection of mathematical, logical, and statistical and arithmetic or algorithm-specific functions. So these are specific functions in general. So here we make use of power regex functions. So which means that these regex functions are specifically tailored for power functions. So these power regexes are used in script modules and expression list to update device power state values or to make transition into a new power state. So for example, we want to move from standby to active state, then we can make use of regex functions. Or if we want to read current power details to generate statistics. So for all these purposes, we can use power regex functions. These regex functions work with most of the data types and have a specific format to be used. So we will look at some of the formats as well. So here we have an example model, and here we can see the power table defined here. We have the active, standby, idle, wait states, and we have also a few custom states added to this power table. And we can see the PLL block in the PLL module, we have an expression list being used to update the power state of that device. So we can see the power update is a regex function which is used here to update the state of that device. So it is used here to update the device power state. And it is based, and we can also see here that it is based on a condition. So if the current power state is same as the required power state, then no power update is done. If it is not same, then we will make the power update to transition the device into the required power state. And here we have a list of few regex power regex functions which can be used in the VisualSim platform to get increased functionality. So we have the power cumulative function, power current function, which is going to give us the current power value for the device. The power manager, which is going to read the power values for all the devices in the model. The power update used to update the state of the model, power update and used to update multiple states of the same device. So if we have multiple levels for the same device, then it can be updated using the power update in regex. So in conclusion, we were able to use VisualSim Architect to do early system level power exploration, which provided accurate results. We can make use of the power table to enter or map the vendor datasheet metrics into the VisualSim platform and run simulations. We can also make use of online resources such as the blogs and articles from reputable websites and online research materials to map the data into the power table state values. The system level analysis has made a huge impact on performance, area, and power analysis, because using it, we were able to see the trade-off that we have to make and what is the expected performance and the power consumption, and these were able to be achieved at an early architectural phase itself. The early system level power studies eliminated all the surprises which could have happened during implementation. We were able to see that for our specific use case that we saw for the multimedia SOC, we could see that with the hardware accelerator added to it, the area was increased as well as the power consumption went above the threshold. So we were able to accommodate for all of these surprises by using the simulation platform's early architecture evaluation. The VisualSim system level power methodology was proven and is effective for different similar situations and use cases. And this covers the session. And if you have any queries or questions, please contact us at info@mirabilisdesign.com. Thank you.